Okay, so good morning again. Lecture number 8. Today we finally get to the macroscopic world and models. But let me just remind you what we've done the last topic. We've seen the LeChatelier-Braun principle as a consequence of some interesting relations that emerge from the fact that stability conditions involve quadratic forms of some of the fundamental where the matrix is second derivatives of the fundamental relation or of some other characteristic function like the Gibbs free energy or the Helmholtz free energy. And as a result of the mathematics of putting a quadratic form in canonical form, we obtain these inequalities that we have also interpreted in the sense of a theorem, because after all this is a theorem. We could call it the LeChatelier-Braun theorem that has two assertions, namely the fact that the system responds to when you move it away from where it is comfortable. So when it is in mutual equilibrium, for example, with a reservoir. And we have seen that there are different types of reservoirs with which the system can be in mutual equilibrium. So the same idea apply for mutual equilibrium with all those kinds of reservoirs. The idea is that the system, if you do something to it from outside, for example, put in energy or put in particles or change the volume, the system reacts in trying to go back to where it was comfortable. So that's the first assertion. So if you put in energy, it will increase its temperature so that it increases its willingness to give away energy and return to equilibrium with the reservoir. But the second assertion, which is a consequence of this additional mass from the canonical form of the quadratic forms, is that it depends, the reaction of the system depends on which direction you take it away from equilibrium. And in particular, if you break conditions for mutual equilibrium. So, for example, if you have if the system can exchange volume, like in the example of the air springs, the system can exchange volume, and suppose that it is in mutual equilibrium also with the thermal reservoir, so at the same temperature. So there are two conditions for mutual equilibrium: quality of pressure and equality of temperature. If you change the volume while breaking both conditions, the system will react stronger than if you just break one condition. And that's the idea. And the difference is important. For example, in the case of the air spring, the difference in you get the reaction makes this volume act as a standard spring, but the spring constant depends on how many conditions for a mutual equilibrium you've broken while changing that volume. And the change may be of the order of, it's 40%. If you do it slowly so that the system has the time to remain in the same temperature So by exchanging energy with the reservoir, it remains in mutual equilibrium. Then you get a milder reaction than if you do it fast. And if you do it fast, you change both the pressure and the temperature, and so the system has two reasons to go back to equilibrium. Okay, so now we finally to the question, well, what's the difference between microscopic systems and macroscopic systems? What do we gain if we make some additional assumptions that will involve having many particles? Okay. So let me start with a few pictures, but also even a more simple idea. So, because there are several ways in which we can see the effect of what happens when we have few particles. For example, consider a single particle and consider the most basic description, which is the quantum mechanics description. In quantum mechanics, you have that the particle is described, the position of the particle is described by a probability density function, which tells you that, so it tells you what is the probability to find, for example, the particle when you make a position experiment in this small interval between x and x plus dx. And in fact, according to quantum mechanics, that all you can predict is the probability. You cannot predict where the particle will show up the next time you call for where are you. Okay, so essentially the state in quantum mechanics is the probability distribution, or the set of probability distributions that allow you to describe all these measurement acts, but in a statistical sense. Okay. You see, the important thing that I want to emphasize today, that is important for our discussion today, is the fact that you find, in order to solve in quantum mechanics this problem, you write the Hamiltonian of your particle or system or particles, and you have to solve an eigenvalue problem to find the eigenfunctions of that Hamiltonian, and you have to face the boundary conditions. So the walls of your system the things that we call external forces are represented by an infinite potential here on both sides, which forces the functions to go to zero at the wall. Okay. Then, of course, if you solve that eigenvalue problem, you find functions that you can look it up in any Wikipedia page. There is the various solutions and various eigenfunctions. And then when the system is in a stable equilibrium state, the overall probability is a mixture of those eigenfunctions. For example, here I took a paper in which there is not one particle, but 4 particles confined in a box like that, and at very low temperature. Now, very low temperature, that mixture of eigenfunctions make the lower eigenvalue ones prevail. And you see here that, so these are the distribution of particles, or probability to find the particles, for various cases, going from a boson, black line, to a fermion, to things in between. The common feature that is important to us is that at the wall goes to zero. So there is that means I would call it a rarefaction effect. You can think of it as a gas, a probability gas, but it's rarefied at the walls. Here is another paper, a review written by Professor Raggi Costantino, who is the mentor of this class. And in another realm, this is not quantum mechanics, it's molecular dynamics, the molecular fluid mechanics. So there is a solid wall, probably made of carbon, and what happens is that the particles, the interaction of the particles due to van der Waals forces, so these are repulsive and attractive forces like Lennard-Jones, and we will talk again about this, but for the moment I presume that you have some ideas about that. Due to these forces, and due to the fact that the wall is a fixed layer, and it imposes the forces that do not move, whereas on the side of the bulk of the fluid, the particles move, and so there is more random action of forces. The ordering imposed by the wall implies an ordering and layering of particles at various distances. There is a first preferred distance, and then there is a second, third, and so on, fading out as the randomness become more important away from the wall. So this is also a sort of wall, I would still call it rarefaction effect, because in very close to between the first layer and the wall, there is nothing. The particles don't like to stay there. This in fluid mechanics has importance because it's related to the problem of the no-slip condition. If you are a fluid mechanicist, when you have few particles, you have to deal with this problem. And this is another example. Again, watching density distributions of a gas. Now here, it's not few particles, it's like 10 to the 5th atoms. It's not very few. Still, in these cases, you see density wall effects with rarefaction very near the wall, and then there are peaks where the particles like to stay near the wall more than in the bulk. Now 10 to the 5th is not small, but it's not large. Okay. So what is, why is this important? And so let's start with, suppose I have two particles like this. Okay. So I have a wall, but on the other side, I have a specular situation in which I have another particle in the same stable equilibrium state. This is the meaning of this part of the figure. Think of just one particle on one side and one particle on the other side. That's okay. Now, suppose I find a way to make that wall that separates the two particles disappear. Okay? So the moment it disappears, particles don't know yet. You just removed it. They're still there. Let's say, oh, hey, there's more room available. There is more volume we can fill. So there will be a spontaneous process whereby the particles will fill that volume and eventually will reach a new stable equilibrium state. Let's say something like that. If we look at it on with the help of the E versus S diagram, which is very useful here, I have drawn the E versus S, the stable equilibrium state curves, fundamental relation of the two systems that we have considered. One is the system in which there is a partition that divides it into two. The other is the system without the partition. And that system without the partition, for that one, we are considering two states. The state we started with, when we just removed the partition, it's a non-equilibrium state, so much that we know that we'll evolve towards the stable equilibrium state. So this point here represents, for the system with the partition system as the initial stable equilibrium state, but it also represents the state of the system without partition, and it's the non-equilibrium state for that system. So here we call system A the one without the partition, and system 2 lambda, I mean lambda plus lambda, so it's 2 lambda, the system with the partitions. The reason I draw them on this same spot, meaning that they have the same energy, same entropy, is a consequence of the idea that I have found a way to remove a partition without perturbing the system, without putting energy in, without any external exchange in no time, so that essentially I don't change any of the properties. Ideally, you could do it. And the fact that I have put this state to the left of the final stable equilibrium state is that, intuitively we know that the particles will evolve by filling the entire space. So that's the direction in which the system will evolve, not vice versa. If I have put this state on the other side, it would mean that the system would separate spontaneously, which doesn't happen. Okay. So the first consequence of this is that the entropy of the stable equilibrium state of the two particles that have the same energy, initial energy, because this system it all happened in an isolated system. So the entropy of the final stable equilibrium state is greater than the initial entropy of this state or also of this non-equilibrium state. That is by the principle of entropy on decrease. A spontaneous process goes only in the direction of increasing entropy for an isolated system. So what is that changes when you have many particles? Somehow I have already used this idea here. When you have many particles, because here I go from 1 to 2 particles, the slope of this probability distribution at the wall becomes steeper. So in other words, the more particles you have, the smaller is the rarefaction layer next to the wall. And as a result, you see here, you see the difference with, and like where the differences are between the probability distribution of equistable equilibrium states. Here, they're remarkable. But as this distribution becomes sharp, so eventually you have an almost flat distribution in the bulk of your system and a sharp, very thin, maybe we call it boundary layer or wall layer, rarefaction layer. So even at the center, this region is very small. That means that the two stable equilibrium state curves get closer to one another. And in the limit of many particles, you can neglect this difference. So you can neglect this fact. You can approximate the properties of system with the partitions with the properties of the system without the partition. Or, if you are interested, you can model the system without the partition as if it had the partitions. This is very important. We will return to this when we go here. It's very important, for example, fluid mechanics, because you have a big box or eye for whatever flow you're considering, and you want to work in terms of fluid elements, fluid parcels that are small, load enough many more with respect to the big system, so that it will cool, but not small enough to have this kind of effects. Needed to have enough particles inside here so that you can consider it consider the continuum hypothesis, but it return to the continuum hypothesis. What I'm interested now in saying is that when I consider like Q element here, I am going to apply models like the local equilibrium model, and you will assign to this in the properties of a system in which the particles are closed by physical words. So you approximate the fluid element as locally has the properties of a fluid element separated from the rest by physical words. How do you do that? By insert partition, three-dimensional, make a small three-dimensional box, take this system side, study how it behaves when it has certain temperatures, pressures, the energy, and so on. Okay, and then I say, well, the properties of this are the same as that. Forgetting about Wolff's effect. But this idea of physically inserting or removing partitions in the fact doesn't change the properties of your system is fundamental in our industry continua at the macroscopic level. Okay. But in principle, we should know that if you reflex with a blend with two particles, then it will make me in trouble playing this game. And so your assumption that using made, which involves local equilibrium, field hypothesis, also should take care about the many particles of fluxes. All right, so let's see what we gain in the limit of many particles, and we'll go back to computing this energy within partitions. Let's see what we gain. So here's a more schematic idea. So suppose we have our system A is this one, where we have whatever particles, a given volume. Volume here is important because, of course, it has to be able to finish system. Also, you see, when we are in this limit, since the rarefaction effects become unimportant to the boundary, essentially the geometry of your container loses importance. For example, here, where in this this picture here shows very well that the geometry of your container does play a big role. So if you have, if you go to this paper, there are other geometries that are shown, nice pictures. You see that the way particles layer out, this Mercury layer layers walls, depends, of course, on the shape of the container. And therefore, the properties of stable equilibrium depend on the shape. But in the limit in which those wall effects become important, only the overall volume of the container, not the details, are important. Because in the bulk, the distribution becomes uniform. So it's uniform everywhere. Okay. So here, suppose we have our system, and suppose we partition it into lambda partitions. Here we call it lambda, later we'll call it n. So that means that on this side, this is a composite system. It's still in stable equilibrium state. Each one is in a stable equilibrium state, like this is the system we started on here on the blackboard. And we assume that we have partitioned in such a way that not only the volume, but also number of particles is exactly 1 over lambda. The overall, the volume is 1 over lambda overall, and the energy is 1 over lambda. All right. So now remember what the fundamental relation means. For example, here, fundamental relation means that it gives us the properties of all the stable equilibrium states as a function of energy, volume, and amount. So it is valid. It is a function, the same functional form, maybe e squared, e cubed, log of n, things like that. So it's the same function for all values of E, V, and N. So I can compute it also for E, but also for E over lambda. The same function, if it is the same mixture of substances, for example, for lot of energy or small energy, large volume, small volume, many particles, few particles. As long as this few doesn't get too few, that's okay. I mean, it's okay what we are going to say. So at this stage, it's okay in general. But what we said here is that these curves, this is a partition curve. It's the summation, it's this side. So it's this much for each subsystem. So if you have lambda of those, you multiply it by lambda times S, because S is an additive property. So you can, the entropy of the overall is the sum of the entropies of the parts. And so this composite system has an entropy lambda S. And this S of lambda. Whereas system A has an entropy S of A. In general, this has bigger entropy than that, but in the limit of many particles, this difference becomes unimportant, and so we can approximate that the two are equal. That's what we call the simple system model. You don't find it around with this name except in our book. Perhaps the choice of the name wasn't so fortunate, but it expresses what you find under the title of thermodynamic limit in physics. So that's how it's called, this idea. It is a limit, because now look what we are going to do. We choose a finite value for lambda, so we partition the system in a finite number of partitions, and it has to be finite in order for the number of particles inside each to become not too small. Yet, if lambda can be large enough, practical purpose, so that you have many particles, 10 to the 23, and if that lambda could be, say, 1 million, and still in each partition you have 10 to the 17. So that means still a lot of particles. So from the practical point of view, when you have so many particles, you can think that this lambda can be any number. Yes, it could be integer, but I mean, who cares? Between the integers, there are the reals, so let's just make it real. Okay? So you make this mathematical assumption. Essentially, take this formula here and make it valid. Make it as valid for any lambda, integer or real, doesn't matter. So you formally assume that the fundamental relation has this property, and this property for a function in mathematics. It's called the homogeneity of first degree. So the fundamental relation is a homogeneous function of first degree in all of its independent variables. Divide each one by but the same lambda. Then multiply the result by lambda, you get the value of the function for the original values of the independent properties. Right? This is an important assumption, of course. It's a heavy assumption, which has this physics for us to support it. And when you do it, we gain one relation. We're going to prove it in a moment, which is called the Euler relation. And notice also, I changed the letter for energy from E to U. And we're also going to call it internal energy for the station. So as soon as we say internal energy, we say, aha, okay, we are within the simple system model approximation. All right, so how do we prove that relation? Well, it's simple. One way is, since it has to be true for all lambdas, take the partial derivative of this with respect to lambda. Now, is it, yeah, okay. I think there is something something fishy in this. But there's something fishy in this view graph, something missing. Sorry about that. But okay, so when you take the partial derivative with respect to lambda of this thing, you get u because of this lambda here. And then you have to take it. You have lambda that multiplies the derivative of u with respect to s times the derivative of s of this with respect to lambda. So it's -1 over lambda squared and so on. So yeah, this is wrong view graph. Sorry, I'll correct it. And then in the end of this derivative, you take lambda equals to 1. And here comes this relation. It's better done in the book than in this view graph. Sorry, but okay. And what is another consequence of these derivatives? Are okay now. This is another the main consequence of the Euler relation. Is that we can define, it makes sense to define specific properties. So for example, I have the energy, I'm not going to call it E, I'll call it U. And suppose I have n particles, and then is the sum of all the particles that are present total, so this is pi. That's the number. So this, I'm going probably example specific molar energy. I do the same for the enthalpy of the volume and for the amounts. Well, the amount of substance I divided by total is becomes the mole fraction of that. Okay. So now I'm going to express, I want to see how the specific molar energy, that represents how much energy I have with unit number of parts. Instead of n, I put the denominator in the m, the mass, that would be the specific energy with mass. So how much energy I have, sorry, kilogram of substance. Okay. So from the definition and of U, so U is a function of S, V, and N. But S can be written here as small s, specific times the amount, N times S. And so volume, so the volume can be written as N times lowercase v, and the amounts can be written as the N times the mole fractions. So if I look at this expression here, I see that the specific energy does depend on the specific entropy, specific volume, the mole fraction, but it also depends on N, because the N appears all in several places here, right? So that means, for example, that I have 1 kilogram, a given amount of substance that has a certain energy, a certain specific energy. But if I have 2 kilograms, the energy per kilogram may not be the same if it depends on N. It's like here. I have another 1 part because I have so many properties. I could have in my side. Happy. Current. If I have 2 particles, they have properties that not stay in that with the same similarly in theory, like I saw that you would to the set up and would then form with loud, but actually. So for small systems, this dependence on N is there, and it is represented by the fundamental relation. That's so you need to measure it. So for small systems, you have to measure. It's not enough to measure the unit of a substance, like 1 kilogram. So you measure the properties of water called the spin modes. You measure 1 kilogram and you're done. Because when you have 2 kilograms, you just multiply by 2. That's good in the macroscopic limit. But when you have 100 molecules of water, it's not just twice the properties of 100 molecules. You have to see how it depends, how those properties depend also on the amount. But in the limit of many particles, that dependence vanishes. So this proof, which takes again the partial derivative of u with respect to n, so you want to see how much is that. Well, that dependence is equal to, if you do the derivatives and let you do it, it's minus 1 over n squared times, you remember what was this? We should add there. But Euler characteristic function. That term in parentheses is what we call the Euler characteristic. So here what we say is that the specific energy of a system at stable equilibrium depends on the number of parts that it is measured by the Euler characteristic. But in the limit, as n goes to infinity, so that's simple system goes to zero. Because the Euler relation just says that this is equal to zero. See? That relation here, or what we call the Euler relation, is equivalent to saying Euler characteristic function equals zero. So that's what we gain. We gain one more relation. And you will think already so many things from just watching the side of the fundamental relation. Now we have another one. You can imagine that you can extract also a lot of additional information. For example, one way, which is now equivalent to the Euler relation, is to take its differential and subtract from it the Gibbs relation, which is the differential of the fundamental relation. The result is called Gibbs-Duhem relation, and it is this one. It's a relation in which you see the independent differentials are temperature, pressure, and the chemical potentials. So these are the properties that determine the conditions for a virtual equilibrium. Okay. Once we have this idea, we can also proceed with defining another kind of interaction, which is the bulk flow interaction. Then using this idea that now that I have a system of many parts to power down, I have to begin that, but initially that I can consider a fluid element, and I can assign to it properties as if it were separated by physical walls. So, right, instead of doing it like a cube, I consider a sphere, but that's the same idea. So suppose that locally I have doing that, and it is in a stable equilibrium set. Well, this middle box. There is not particles, so that's the rarefaction effects are lots of pocket. This little box is in a stable equilibrium. Now, if I look at the fluid element from a different frame of reference, for example, y that moves, I look at it from the frame of reference, moves this way, it goes the other way. It applies a velocity back to that frame of reference. And associated with that velocity is the kinetic energy. In addition, if I look at it from an accelerated reference frame, then that has the same acceleration as the gravity, g, then it acquires also potential energy. Is mechanics. So the idea is this. Okay, now including mechanics, see the actions in which particles cross the boundary between two systems, there is movement. Choose as reference plane, and that's of the boundary where the particles that are crossing. They have velocity. But for each of these particles, I can always find the reference frame in which it is not moving. And even if it is in presence of a gravitational field, for each of these particles, I can find an accelerated frame where it is not moving. With respect to those frames, there is no kinetic energy and no potential energy. So somehow, this kinetic energy and potential energy has effect that can be added or removed by just changing the reference frame. Clearly, that doesn't change the internal properties of the stuff. It doesn't change the energy. Yes, it does change the energy, but it doesn't change the other properties like atoms. So this is the model that we make, that we call bulk flow state, bulk flow local equilibrium state. We assign to the fluid elements the property of a local stable equilibrium. Or we assume that there is some reference plane with respect to which it is not moving and we blow potential energy, and this is that we subtract, in the sense, kinetic energy and potential energy with respect to this laboratory plane. That thing, that energy which satisfies the fundamental relation of stable equilibrium. In that sense, it has temperature, it has a pressure, it has lobes of a fundamental relation. Okay, so that's step one, defines a local equilibrium model. Step two is that if you have a boundary between two systems, for example, you have a pipe that brings fluid elements inside your system. So we usually, this is an open system, call it an open system. And we usually represent as a boundary, the formal boundary, as imagine it's in our mind, there is a boundary between the pipe and the system. But this boundary isn't physical. Yet, in order to model the interaction, we suppose it is physical. Suppose we can put a physical partition, which we are allowed because we are within the simple system model. So let me put at a time instant t, let me put a partition that separates that amount of fluid that is going to cross this boundary in the next time interval delta t or dt. So now it's here, later is there. And it's physically separated by partition. At no cost, I have put in that partition. Okay. Then what happens? If I look at from the fluid element, the fluid parcel that is coming, that is crossing here, from a reference frame that moves with its velocity, I am assuming, for simplicity here, that there is a flat velocity of pipe, or in fact, conserve the same velocity. or if not, you should make it for smaller parcels who also single out the velocity profile. So, but for simplicity, let's suppose we look at just one element, and so that as its velocity, and look at it from the reference frame from which you see it as not moving. Okay? This partition that you put in is a partition that separates two systems that are in mutual equilibrium. They have the same pressure and temperature. Particularly, the pressure is the same, that partition. Even if it could move, it wouldn't move because all the fluids that are coming in the pipe here have the same pressure. But if you now make the energy balance, and here is the details of making the energy balance for this composite system, of the system which is receiving that amount of fluid plus this fluid that will eventually get in. So now that we have separated it with a physical partition, this partition makes it a legitimate system. So the composite system A plus B prime is well separated from the rest because it has a wall and it always satisfied our definition of system in which we get external forces with certain kind. Okay, so for these kind of systems, which are closed system now, we have already introduced the energy balance. We can do the energy balance, which involves saying that the final energy minus the initial energy is equal to the energy exchanged via interactions. And here, there is only one interaction. It's the fact that there is a pressure acting on a moving piston, moving boundary. And that is a work. So this is the work. Okay? That means that now we play additivity. In the final state, we note that in system B prime, there is nothing left. The system B prime is now between this fixed boundary and the moving boundary. If you want, we could say that, to be more precise, I should say that at initial time, at time t, in order for system B prime to be a system, I have to have introduced physical boundary here. Then I remove it, I let things go, and in the end, I put again the physical boundary here. But there is nothing between the two boundaries. So the energy and entropy there are zero. And again, in order to do the adding or removing partitions, I need to be within the simple system model. Okay, so to make the long story shorter, here is the expression for the work. It's pressure times the area times the displacement. And you can show that it is proportional to the specific volume times the pressure times the amount of that fluid parcel that has been exchanged. And in the end of the story, you see that this work, which we usually call the Pulsion work, adds a contribution to the energy that is brought into system A. It's not only the internal energy of fluid, not only its kinetic energy and potential energy, but also this Pulsion work. And that is why in a bulk flow interaction, it's U internal energy plus PV, which, if we recall, it corresponds to the definition of that characteristic function that we call the enthalpy, that enters into the expression that says how much energy is transferred in this kind of interaction. Of course, you can do the same when the parcel is going from inside to outside. And therefore, we get this summary of defining properties for the bulk flow interaction. It contributes mass to the system, because I have material that goes in. By the mass balance, you can write it this way. Energy, here's the enthalpy, and also entropy. The entropy is just the entropy that the fluid element has, and simply translate from outside to inside. Translates. Okay, in, out. You can also do this per unit time. And you can, therefore, now with this additional type of interaction, you can write balance equations for a system that is subject to all sorts of interactions. For example, here we have a heat at or temperature TA. Typically, we use the letter A or the letter 0 for the environmental conditions. Here we have a heat interaction at some other temperature, maybe cold. This one at another temperature. We may have work interactions of various types, like a shaft bringing in mechanical energy, electrical wires bringing in electrical energy. These are all work equivalent. Or a moving boundary against the pressure of the atmosphere. That is also a work interaction. And plus we may have many bulk flow interactions. And as we have seen, in order to characterize a bulk flow interaction, we need to characterize the bulk flow states of the fluid elements that are carried in and out. So you need the enthalpy, the local enthalpy, the local entropy, the velocity of the fluid elements, and the local height in the gravitational field, so that you can compute the potential. Of course, subject to all these interactions is going to be it's not going to be easy to balance them so that you keep the energy the same, the entropy the same, the volume the same, the mass the same, which would be required to keep the system in a steady state. But very often, that's exactly what you do. For example, this is a power plant, and you want to operate it in such a way that it doesn't consume itself, it simply processes stuff. So you need to balance what goes in with what goes out. And while you do that, it definitely, most of the times, produce entropy by irreversibility. So these are the balance equation for mass. The rate of change of the mass is the net mass flow rates that go in and out. Here, to simplify the notation, I consider m dot with the arrow just in, so it's positive, it's in. That means that if I want to represent something going out, I will need the negative. Or you could split this summation into two sums and put on one sum the masses that go in and minus the summation of the masses that go out. That's set. So also this for the energy, the rate of change of the energy is equal to the net amount of energy transferred by interactions. Here are the heats, the works, here are the bulk flows. And for the entropy, the rate of change of the entropy of the system is, first term here is the entropy exchanged, either via the bulk flow interactions or via the heats. And then, well, how about this sign? What do you think? That's an error, okay? The entropy plus the entropy produced by irreversibility. That needs to be corrected. Just, I probably left it there to see if I'm awake enough and you are awake enough to spot it, but so we did. And once we have these balance equations, we can manipulate them or solve problems in a large community of engineers that have played with these equations. There's developed this idea of exergy and exergy analysis of energy systems. It adds nothing to these equations, except perhaps it helps in reading them. It adds nothing because it is based on a linear combination of these equations. So mathematically, all the information is contained in here. So this is the basic. You definitely need to make an energy balance and an entropy balance. If you don't like working with entropy, and you prefer to work with a linear combination of energy and entropy, fine, then you call it Exergy balance. And so one way to combine these equations is to take one of these forms that is to take the second equation, the entropy balance equation, multiply it by some temperature, and it is convenient to choose the temperature of one of your heat interaction, and it's even more convenient to choose the temperature of the heat interaction that is considered free of charge. For example, if your machinery operates in in an environment like the air, your air conditioning at home works in the air and uses and dumps heat in the environment, I would use that temperature as the temperature that I use in this linear combination. If instead your power plant is cooled by the water of the river, I would use the temperature of the river. In any case, so you take that, multiply, and then subtract it from the energy balance. And if you, I think here also you have to be a little, I should have been a little more careful in making explicitly the work, write separately the work related to the P times rate of change of order, like the PV, PA times rate of change of volume should have been singled out here. Maybe I'll do it later on the slides, just for the slides, and when I correct also the minus sign here, so that work term can go on this side of the equation and make this PA times dB retain. Yes. All right, so here is an Exergy balance equation, and the Exergy is a topic that we need to discuss. I will not make the story very long, but it's part of thermodynamics, so it is a good idea to discuss it. Also because it brings several useful ideas about how to define efficiencies of energy conversion devices, and so it is important in the mechanical engineering department. We will see. Okay, we already have seen that combinations like that. I think we use the letter T, capital Phi, to represent his availability function, E minus T Rs plus P Rv. So this says that's the rate of change of the availability. But exergy and availability are the same idea, same concept. There's two words for the same idea. Heat times Carnot coefficient. And the Carnot coefficient is between the temperature of what I've chosen as my environment and the temperature at which the heat is exchanged. This represents, for a given Carnot engine, the maximum work that you could extract by exploiting that heat interaction, having available an environment at temperature T0. And so this is the exergy associated with that heat interaction at temperature T0. Work appears directly, not multiplied, not corrected, because work is already available to, let's say, if you have some work, you can do useful things directly. You don't have to convert it. The work is already, in a sense, exergy. Because the word exergy really means the essential part of the energy, so the useful fraction of the energy that it's either within your system or an energy transferred. So the concept applies both for the additive properties of the system, that energy is, or the modes of energy transfer. Heat, work, and here is also the exergy expression for the bulk flow interactions. And out of this, do the proper sign here, you get a minus, and here is correct, minus T naught times S dot irreversible. This is the dissipation, the terms that represents the destruction of exergy. And like entropy cannot be destroyed, exergy cannot be created. You can only destroy it. So they are related. So irreversibility, to do things reversibly, you don't create entropy and you don't destroy exergy. You do things irreversibly. You create entropy and destroy some exergy. That's the idea. And so since we are at this business of exergy, let's just do it. We have already done few lectures ago the first law and second law efficiencies for heat engines, refrigerator units, and heat pumps. So this is just a summary of the same equations that we have already seen up there. Just notice that the first law efficiencies are a ratio where you put at the numerator an energy and at the denominator another energy. Typically, the numerator is the useful effect that you want, and the denominator is the resource that you are using, and energy-wise. Instead, a second law efficiency, you put at the numerator what you want to achieve, and at the denominator, the minimum expenditure that you need to pay in order to achieve that, which is typically done, minimum in the sense of thermodynamics, of course, and so it's the reversible cake. Not saying this is the practical optimum, because in practice, you don't want to operate reversibly or objective. Is very to operate reversibly, because if you operate reversibly, most of the times you have to do it in such limiting conditions that you get nothing. So in practice, what you want to optimize is power, or the combination of power and efficiency, depending on the cost of equipment. Because, of course, the more you put in terms of sophisticated equipment, you may achieve higher efficiencies, but the cost may kill you, so you have to compromise. Therefore, there are other terms in the equation of optimization in terms of practical. And so here we are just talking about this is the limitation of the second law efficiency, is that it gives in the denominator, which is your term of comparison, the reversible process, which may be too far away from practicality. One sort of halfway solution would be to put there the work required by the best available technology to do that particular job. In that way, at least you compare the efficiency of your device with the efficiency of the best available technology. And of course, if your device is better, your efficiency will be higher than 1, and eventually your technology will impact and will become the best technology class too. All right, so this view graph simply summarizes again the idea of first law, where you do energy associated with the useful effects divided by the energy associated with the resource that you have used, which could be burning a fuel or using solar energy. And here for the second law, you can cast it for the second law efficiency. You can cast it by saying that I put them also the exergy associated with the useful effect, because the exergy represents the work equivalent of that useful effect, and then you put at the denominator the exergy associated with the resource that you've used. You can, if you reason it out, you realize that this is equivalent to putting here the energy of the useful effect, and below the minimum resource you should use in order to obtain that, which is, I think, written here. See, this form of the second law efficiency is also equivalent once you do the balance equations and obtain the expression for the reversible work as a ratio of exergies. So, for example, for the heat engine, if the ratio of the exergy of your product, which is work, so just pure exergy, divided by the exergy of the resource, which is the heat times the Carnot coefficient. And notice that the Carnot coefficient has to be computed using the temperature as environment, the temperature of the cold reservoir, which you're using as an environment, or as the thing where you dump your entropy. And similarly, for a refrigerator, this definition is equivalent to the definition in which you have exergies, numerator and denominator. Now, for a refrigerator, this is the exergy of cooling with a cooling load QB times this is equivalent to a Carnot coefficient. With minus signs becomes a Carnot coefficient. But here now you see the Carnot coefficient with the T at the numerator, so the T of the environment now is the hot, because in the refrigerator you are pumping entropy to the environment, which is hotter than the refrigerator cell. And similarly here for the heat pump. So going back to this idea of exergy, so the word exergy, or the word availability, in the old times there were fights. Well, how should we call it? There has been, I participated in conferences where people were really fight. Nowadays, I think everybody is more loose about the idea, and then it's just use exergy or availability. It doesn't really matter. It's a generic concept of. So exergy does not have one definition. Different forms of exergy. For example, we encountered many already. For example, the adiabatic availability is a form is one exergy. It's the exergy associated with when you restrict yourselves to weight processes. Well, you can call that like an adiabatic system, a system that undergoes all the weight processes. You can call it adiabatic. Or we have seen that if your system is in combination with a thermal reservoir, the maximum you can do, the maximum work you can do depends on the type of reservoir. The reservoir has fixed volume. We have this that we call available energy, omega R. But then we have defined also available energy with respect to other kinds of reservoirs. where the reservoir can change also volume, or maybe the osmotic reservoir where you can exchange it through a semi-permeable membrane only one type of substance, or a completely open exchange in which your system can exchange volume and any of the amounts. These are all exergies. Different formulas, same word. Work is just pure exergy. A heat interaction, just said. So the exergy associated with the heat interaction at temperature PQ is given by the heat times the Carnot coefficient. Exergy requires, as before here, requires a reservoir as a reference in some cases, not in here. For a heat interaction, it does require that. And need to specify what kind of, so you need to specify, to choose a temperature. So it's relative, and exergy is relative to a choice of a particular reference environmental temperature. Yes. So even that makes it a broad concept. So you can define the exergy for a cooling, heating, cooling interaction. And for example, suppose you have a machinery that operates like a Carnot engine, and this is simple case in which we have two reservoirs. But suppose that neither the hot reservoir nor the cold reservoir are environmental reservoirs. For example, this cold reservoir could be your house, the house that you want to warm up. You want to be at 70 Fahrenheit or 21 C in your house. And one way to heat up your house, it's actually one of the best ways in terms of, from the point of view of thermodynamics, is to use cogeneration. You use some costly heat source. For example, okay, this is a reservoir, so it's not exactly, so it's not a proper example, but usually you buy gas to heat up water, and then you have your water circulating like here, heating elements, and that hot water is going to heat up the air in your room. So you're using a gas with which you could reach very high temperatures. And all you do is, by a series of heat transfers, use it to produce something at a temperature which is very close to the environmental temperature. That's a very dissipated way of doing it. We have been doing it all for a long time like that. We're still doing it. Like that's the way it's done in my apartment building where I live right now. And but that's not the good way. It's a very inefficient way. Cogeneration is the idea that you take that high level energy And before you you do as much as you can with it. You do, for example, run a power plant or run a plant or run a engine. For example, you could run a car engine. This is our called total energy modules, like car or truck engines, or maybe ship engines, depending on the size, where you burn your fuel, make mechanical energy. With that mechanical energy, you produce electricity. And then, since your engine needs to dump entropy somewhere, instead of dumping it directly into the environment, you dump it into the heating system of your house. And then it will, your house, take care of dumping the energy, the leaks, to the environment. So you get this heating as a byproduct or as one of the two products of your system, which is a combined heat and power. So it's called cogeneration, or CHP solution. And in this way, you've used that energy at best. So this would be, say, the available best available technology. For example, in the town where I worked 30 years longer, which is Brescia in Italy, this idea has been taken very seriously starting in 1973. And now about 95% of the volume of the town, and it's a town with the size of Boston, it's heated in this way, with cogeneration power plants that dump energy into a district heating system. So you get this hot water going around the town, under the roads, and reaching all the houses, and then with heat exchangers, you do the heat. More recently, 20 years ago, they also added a more complex system in which you also not only use fossil fuels, but you use also waste. You burn the trash that is not recyclable, and they also integrated with the hybrid way with some solar. So it's an entire system aimed to efficiency for heating the homes. I know that many are thinking about doing things also in the States, but here the problem has been that the reason that these things have not evolved is the cheaper cost of energy addition. One incentive for improving efficiency is the cost of energy. Higher the cost, people invest to spend less. Yeah. Once we are. We would. I'm not answer that. I'm in. Okay. Good. At some point in the year, the trail at the earlier than the nest. It's great that it wanted. It was glad to know it. Yeah. Yeah, probably. I thought that somebody was thinking of also, doing it for the town. The problem is that it takes a lot of investment, and the way it got started in Brescia was that the municipal company was the company that would run also the roads, would run a lot of public services, including transportation, and so they could sort of decide and move quickly about doing, because they were the people working on the roads. So, putting pipes, because you need to put large pipes under this. If you do it internally, it is easier. And also they did it in such a way that there's another issue is people would want to be to get connected to the district heating system, but sometimes it's more efficient to start with big buildings and then go to smaller ones. So this kind of decisions are a bit political, and so these are issues. Okay. So we are late. So see you next time.